the Alpha 21264 microprocessor, the Alpha 21264 owes its high performance to high clock speed. Many forms of out of order and speculative execution and high bandwidth memory systems. Alpha, the early Kessler Compact Computer Corporation. Alpha microprocessors have been performance leaders and they are introduced in 1992. The first generation 21064 and the later 164 raises the expectation for the newest generation. Performance leadership was again a goal of the 21264 T9 team. Benchmark score of the 30 plus spec into 95 and 58 plus spec FT95 offered convincing the evidence for that 21264 archived this goal and will continue to set up performance standard. Unique combination of high clock speed and advanced microarchitecture techniques, including many forms of out-of-order and speculative execution, provide exceptional core computational performance in 21264. The processor also features a high bandwidth memory that quickly delivers data values to the execution core, providing robust performance for a wide range of applications, including those without a cache locality. The advanced performance levels are attained while maintaining uninstalled appropriate base. All alpha generation are upward compatible database and real-time visual computing and data mining, the medical meaning imaging and specifying scientific technical and many other applications can utilize the outstanding performance available with the 21264. Architectural highlights. The 21264 is a superscalar microprocessor that can patch and execute up to 4 instructions per cycle. It also features out-of-order execution, so whether the instructions execute as soon as possible and parallel with other non-dependent work, which result in the faster execution because critical path computation start and complete quickly. The processor also employs speculative execution to maximize performance. Speculative patches execute the instructions even though it may not know immediately whether the instruction will be on the final execution path. This is particularly useful, for instance, when the 21264 predict branch prediction at branch directions and speculative execute down the predictive path. Sophisticated branch prediction coupled with speculative and dynamic execution extract instructions parallelism from the applications. With more functional units and these dynamic execution techniques, the processor is 50% to 100% faster than H2164 processors for many applications, even though both generations can fetch at most 4 instructions per cycle. The 21264's memory system also enables high performance levels. On-chip or off-chip caches provide for very long latency data access. Additionally, 21264 can service many parallel memory references to all caches in the hierarchy, as well as to off-chip memory system. This permits very high bandwidth data access. For example, the processor can sustain more than 1.3 gigabytes per second on streaming benchmark. The microprocessor cycle time is 500 to 600 MHz, implemented by a 50 million transistor in a 2.2 volt and a 0.35 micron CMOS process with 6 metal layers and 3.1 square centimeter processor comes in a 587 pin FPGA packages. So it can execute up to 2.4 billion instructions per second. Figure 1 shows a photo of a 21264 highlighting major sections. So figure 1 and figure 2 is a high-level overview of a 21264 pipeline, which has 7 stages. Similar to the earlier in order 21, 164, one notable addition is the map stage that are renamed register to expose the instructions parallelism. This addition is fundamentally to the 21 to 64's out of order techniques. Instruction pipeline, fetch. The instruction pipeline begins with the fast fetch stage, which delivers the 4 instructions to the out-of-order execution engine each cycle. The processor speculatively patches through the line, branch, or jump predictions. Since the predictions are usually accurate, this instruction fetch implementation typically supplies a continuous stream of the good path instructions to keep the functional unit busy with useful work. Two architectural techniques increases fetch efficiency, line and way prediction, and prediction, uh, branch prediction, and a 64 kbyte two-way set associative instruction cache offers much improved level 1 hit rate compared to the 8 kilobyte direct map instruction cache in alpha 21.164. And the line and way prediction. The processors implement the line and way prediction techniques that combine the advantage of set associative behavior and batch bubble elimination. Together with the fast access time of the direct mapped cache, figure 3 next page shows the technique's main features. Each 4 instruction fetch block includes a line and way prediction. The prediction indicates where to fetch the next block of 4 instructions, building which of the two choices allowed by a two-way associative cache. The processor reads out the next instructions using the prediction via the wrap around the path in figure 3, so while in parallel, it completes the validity check for the previous instructions. Note that the address decode branch prediction and cache tag comparison are outside the critical patch loop. So the processor loads the lineup and way the predictors on instruction cache field and they dynamically retain them when they are in an error. The most predictions cost a single cycle. The line and way predictors are correct 85% to 100% of time for most applications. So training is infrequent. So an additional precaution are two high hysteresis counter associated with each fetch block eliminate over training. Training occurs only when the current prediction has been an error multiple times. So the line and way mispredictions are rare. So beyond the speed benefit of the directed cache access, the line and way prediction has other than a benefit. For example, the frequent encounter predictable branches such as loop terminators avoid miss and fetch penalty often associated with the taken branch. So that the processor also trained the line predictor with the address of the jumps and the subroutine code that use directed registers addressing. Code using a dynamically linked library routines will thus benefit after the line predictor is trained with the target. This is important since the pipeline delays required to calculate the direct, indirect, subroutine, jump, address are 8 cycles and more. On instruction caching, forces the instruction fetch engine to check the level 2 as cache or system memory for necessary instructions. The fetch engine prefetches to up to 64 bytes or 16 instructions. So the cache line to tolerate additional latency. The result is very high balance transaction fetching, very balanced instruction fetch, even when the instructions are found in the instruction cache. So for instance, the processor can saturate the available L2 cache bandwidth with the instruction prefetches. Branch prediction. The branch prediction is more important to the 21 to 64 the efficiency than the previous microprocessors for several reasons. First, 7-cycle means predicted cost is slightly higher than the previous generation. Second, the instruction execution engine is faster than the previous generations. Finally, successful branch prediction can utilize the processor's speculative execution capabilities. Good branch prediction avoids the cost of misprediction and capitalizes on the most opportunities to find a parallelism. The 164 could accept 20 in-flight instructions at most, but the 264 can accept 80, offering many more parallelism opportunities. The 264 implements a sophisticated tournament branch prediction scheme. The scheme dynamically chooses between the two types of branch predictors, one using the local history and one using the global history. To predict the direction of the given branch, the result is a tournament branch predictor with better prediction accuracy than larger tables of either individual method. With a 90% to the 100% success rate with the most simulated application and benchmarks. Together, local and global correlations techniques minimize branch predicts so that the processor adapts dynamically choose the best method for each branch. So the figure 4, the detailing the structure of the tournament branch predictor, show the local history predictor path. Through two level structures on the left, the first level holds 10 bits of the branch patterns history for up to 1024 branches. This 10-bit patterns picks from one of the 1024 prediction counters. The global predictor is 4,096 entry tables of 2-bit saturating counters indexed by the path or global history of the last 12 branches. The choice prediction or chooser is also a 4,096 entry table over 2-bit prediction counters indexed by the path history. The local and global branch predictors box describe these techniques in more detail. The process inserts the true branch prediction in the local history table on table 1's branches. The local 1's branches issues and retire. It also trained the correct predictions by updating the reference local and global choice counters at that time. The processor maintained path history with a silo of 12 branch predictions. This silo is speculatively updated before the branch retires and is backed of the mispredict. The out-of-order execution. V21-264 offers out-of-order efficiencies with a higher clock speed than competing designs. Yet, this speed does not restrict the microprocessor's dynamic execution capabilities. The out-of-order execution logic receives 4 fetches instructions every cycle and rename and remap the register to avoid unnecessary dependencies, and Q the instructions in a till operand of the functional unit becomes available. It dynamically issued up to the 6 instructions every cycle, 4 integer instructions and 2 floating point instructions. It also provides an in-order execution order to programmers via in-order instruction retire. Register renaming. Register renaming exposes application instruction parallelism since it eliminated unnecessary dependencies and allowed speculative execution. Register renaming assigns a unique storage location with each write reference to our register. The 21-264 speculatively allocate a register to each instruction with a register region, so that the register only becomes a part of the usual visible architectural register state when the instruction retires commit. This lets the instruction speculative issues and deposit each result into a register file before the instruction retires. Register renaming also eliminates write after write and write after read register dependencies, but preserve or the read after write register dependencies that are necessary for correct computation. The left side of the figure 5 depicts the map or the register name stage in more detail, so the processor maintains the storage of each internal register indicating the user visible registers that are currently associated with a given internal register, if any. Thus, the register renaming is a content addressable memory CAM operation for register sources together with a register allocation for a destination register. All pipeline stages subsequent to a register map stage operate on an internal register rather than a user visible registers. So beyond the 31 integer and the 31 floating point user visible, non-speculative registers, an additional 41 integer and 41 floating point register are available to hold speculative results prior to instruction retirement. So the register mapper stores the register map state for each in-flight instruction so that the machine architecture state can be stored in case a misspeculations occurs. The alpha conditional move instructions must be handled specially by the map stage. These operations conditionally move one of the two source registers into a destination register. This makes the conditional move the only instructions in alpha architecture that require 3 register source, the 2 sources plus the old value of destination register in case the move is not performed. The 21 to 64 split cache each conditional move instructions into 2 and maps them separately, so that these 2 new instructions only have 2 register sources. The first instruction places the move value into an internal register together with the 65th bit indicating the move's ultimate success or failure. The second instructions read the first result and including the 65 bit together with all the destination registers values and produce the final destination register result. Out of order issue queues, the queue logic maintains the 2 lists of pending instructions in separate integer and floating point queues. Each cycle, the queue logic selected from these instructions as their operand become available using register scoreboard based on the internal register numbers. These scoreboards maintain the status of the internal registers by tracking the progress of the single cycle, multi-cycle, and variable cycle memory load instructions. When unfunctional unit or loaded data result become available, the scoreboard unit notifies all instructions in the queue that require the register value. These independent instructions can issue as soon as the bypassed result become available from the functional unit or load. The 20 entry integer queue can issue 4 instructions and the 15 entry floating point queue can issue 2 instructions per cycle. The issue queue is depicted on the right in the figure 5, and the integer queue statistics assigns or slot each instruction to one of the 2 arbiters before the instructions enter the queue. Each arbiter handles 2 of the 4 integer pipes. Each arbiter dynamically issues the oldest 2 queued instructions each cycle. The integer queue slots instruction based on the instruction fetch position to equalize the utilization of the integer execution engines to halves. An instruction cannot switch its arbiters after the static assignment upon early into the queue. The interactions of these arbitration decisions with the structure of the execution pipes are described later. So the integer of the floating point queues issue instructions speculatively. Each queue an arbitrary select and the oldest operand ready and a functional unit ready function unit ready instructions for execution each cycle. Since all the older instructions received priority over the new instructions, speculative issues do not slow down order the less speculative issues. The queues are collapsibly and collapsibly. An entry becomes immediately available once an instruction issue or issue cautious due to the misspeculation. New instructions can enter the issue queue and when there are 4 or more available queue slots. And the new instructions can enter the floating point queue when there are enough available queue slots. Instructions in retire and exception handling. Although instruction issue out of order, instruction fetches retire in order. The in-order retirement mechanism maintains the illusion of in-order execution to the programmer, even though the instructions actually execute out of order. The entire mechanism assigned each mapped instructions a slot and circular in-flight window in fetch order. After the instruction starts executing, it can retire whenever all previous instructions have retires is guaranteed to generate no exception. The retiring insertion makes the instruction non-speculative, gathering that the instruction's effect will be visible to programmers. The 21 to 64 implement a precise exception model using a retire. In order retiring, the programmer does not see the effect of the younger instructions if older instructions have an exception. The retire mechanism also tracks the internal register usage for all in-flight instructions. Each entry in the mechanism contains a storage indicating the internal register that has the old contents of the destination register for the corresponding instructions. This cell register can freed for other use after the instruction retires. After retiring, the old destination register value cannot possibly be needed. All the instructions must have wished to and read their source registers, or your instructions cannot use the old destination register value. An exception causes all younger instructions in the flight window to be squashes. These instructions are moved from the old queues in the system. The register map is backed up to the state before the last squashes instruction using a saved map state. The map state for each in-flight instruction is maintained, so it is easily restored. The register allocated by the squashes instruction becomes immediately available. The retire mechanism has a large and 80 instruction in-flight window. This means that up to 80 instructions can be in partial state of the completion at any time, allowing for a significant execution concurrency and latency hiding. This is particularly true since the memory system can track an additional 32 in-flight loads and 32 in-flight source. Table 1 shows the minimum latency in number of cycles from an issue and retire eligibility for different instruction classes. The retire mechanism can retire almost 11 instructions in a single cycle, and it can sustain a rate of 8 per cycle over short periods. The execution engine Figure 6 depicts the six execution pipelines. Each pipeline is physically placed above or below its corresponding register file. The 21 to 64 split the integer register files into two clusters that contain the duplicate of the 80th entry register file. The two pipes access a single register file to form a cluster, and the two clusters combine to support the four-way integer instruction execution. This clustering makes the design simpler faster, although it costs the cycles of latency to broadcast the region from an integer cluster to other cluster. The upper upline from a two integer cluster in Figure 6 are managed by the same issue queue arbiter, as are the two all-over pipelines. So the integer q statistically slots instructions to either the upper or lower pipeline arbiters. It then dynamically selects which cluster to execute an instruction on, left or right. The performance cost to the register, the clustering and issue queue arbitration and simplification are small, a few percent or less compared to idealized unclustered implementation in most applications. There are multiple reasons for minimal performance effect. First of all, many operations such as loads and stores, the static issue queue assignments is not a restriction, since they can only execute in either the upper or lower pipeline. Second, critical path computation tend to execute on the same cluster. So this issue queue prefers older instructions, so more critical instructions incur fewer close cluster delays. An instruction can usually issue first on the same cluster and produce the result. This integer pipeline architecture set the result to provide much of the implementation simplicity, lower risk, and higher speed of the two issues machine with performance benefit of the four-way integer issue. Figure 6 also shows the floating execution pipes configuration. A single cluster has two floating point execution pipes. With a single 72 entry register file, the 21 to 64 includes a new functional unit not present in a prior alpha microprocessors. The motion video instructions MVI uses speed many forms of image processing. A fully pipelined integer multiple unit, integer population count and leading trail zero count unit, PLG, a floating point square root functional unit, and instruction move to integer values directly between the two floating point and an integer register are included. So the processor also provides more complete hardware-supported IEEE floating point standard, including precise exceptions, NAN, and infinity processing, and support for processing as the normal region of 0. So the table 2 shows the same instruction latencies issues the product to the consumer, and these latencies are achieved through the regional bypassing. So next section is a internal memory system. The internal memory system supports many in-flight memory references and out-of-order operation. It can service up to 2 memory references from the integer execution pipes every cycle. These 2 memory references are out of the order issues. The memory system simultaneously tracks up to 32 in-flight loads, 32 in-flight stores, and 8 in-flight instructions or data cache misses. It also has a 64 kilobyte the two-way set associated data caches. This cache has lower miss rate than 8 kilobytes, and a direct mapped cache in the earlier 21.164. The end result is a high bandwidth and low latency memory system. Data path. The 21 to 64 supports any combination of 2 loads over stores per cycle without a conflict. The load cache is double pumped implement the necessary to port. That means that a data cache is referenced twice each cycle, once per each of the 2 clock phases. In fact, the data cache operates at twice the frequency of the process clock, an important feature of the 21 to 64 memory systems. Figure 7 depicts the memory system's internal data path. The two 64-bit data buses are part of the internal memory system. Each loader receives data via these buses from the data cache, the speculative store data buffers, or external system or L2 field. The store first transfers their data across the data buses into the speculative store buffer, and the store data remains in a speculative store buffer until the stores retire. And once they retire, the data is written dumped into a data cache on either cache cycles. Each dump can write 128 bits into the cache, since 2 stores can merge into one dump. Dumps use the double dump data cache to implement a read, modify, write sequence. Read, modify, write sequence is required on a store to update the SSD ECC that allows correct of the single bit errors. Stores can forward their data to the subsequent load while they reside in the speculative store data buffer. Load instructions as can compare their age and address against these pending stores. On match, the appropriate store data is put the data bus rather than the data from the data cache. And in fact, the speculative store data buffer performs the renamed function from the perspective of the younger load. It appears that the stores write into the data cache immediately. However, the scarce stores are removed from the speculative store data buffer before they affect the final cache state. Figure 7 shows how data is brought out of the internal memory system, and the field data arrives on the data buses. Appending loads the sample the data to write into regular file in parallel. The cache's instruction order data also fill using the same data, but same bus data. The data cache is right back, so field is also its double dump capability. The previous cache content shall read out in the same cycle, and data fill out is written in. The bus interface units capture this victim data and later write it back. So address and control structures. The internal memory system maintains authority to entry load queue, LD and authority to be entry stores queue, ST that manages references while they are in flight. The LD and ST position loads stores in the queue and fetch order. So the order, although they enter the queue and when they issued out of order, loads exit the LD and fetch order after loads retire and load data has been returned. Stores exit the ST and fetch order after they retire dump into the data cache. New cache check their address and age. Again, the order reference dual ported address CAM right to resolve the read after read after read after read and read after read, read after write, write after read, and write after write is inherent in a fully out of order memory system. For instance, to detect memory read after write hazard, LDQ must compare the addresses when store issues. Whenever an older store issues after a younger load to same memory address, the LDQ must squash the load and the load got wrong data. The 21-64 response to this hazard describes more detail in a later section. The STQ-CAM is logic control the speculative store data buffer. It enables the bypass of the speculative store to the load when a younger load issues after a older store. Figure 8 shows an example scheduling of the memory system, as including the both data buses and bus cache tags, both ports of the data cache array itself, 9 load issues, L1 to L5 and line, pieces of 9 stores, S1 to S9, and pieces of little fields, each requiring 4 data bus cycles to get the required 64 bytes. F1 to F3 are included. Load references both data cache tags and array in their pipeline stage 6. And then the load result uses the data bus 1 cycle later in their stage 7. For region figure 8, load and L6 and L7 are in their stage 6 from figure 2 in cycle 13, and then their stage 7 in cycle 14. And the stores are similar to load except that they do not use the cache array, they retire. For example, S5 uses tags in cycle 1 and figure 6 but does not write into the data cache until cycle 16. The field patterns from the figure corresponds to the field from the fastest possible L2 cache. That the cache cross the data buses in cycle 0 gets skewed to cycle 2, written into the cache. This skew is for frequency regions only. The field data could have been written in cycle 1 instead, but pipeline conflict would allow fewer load and storage issues. In that case, fields only need to update the cache tags once per block. This leaves data change tags more light, either within the array or the data bus. Cycle 7, 10, and 16 in the example each shows the two stores that merge into a single cache dump. Note that the dump in a cycle 7, S1 and S2, writing into the data cache array, could not have occurred in a cycle 6 to 7, 1 to 6 because the cache array is busy with field or load issues in each cache. Each case, the cache dumps can happen when only stores the issue, such as on cycle 10, load L4, L4 and L5, and cycle 5 are a special case. Note how these two loads only use the cache tag. These loads decouple the cache tag lookup from a data array and a data bus use, so taking advantage of either data cache tags during field. This decoupling is particularly useful than a miss in the data cache, since that case the cache array lookup and the data bus transfer of the load issue slot are avoided. Decoupled loads maximize the available bandwidth for each cache misses, since they eliminate the unnecessary cache accesses. So the internal memory system also contains an entry miss address file, MAF. Each entry tracks outstanding miss field to a 64-byte cache block. The multiple load and store misses to the same cache block can emerge and be satisfied of single MAF entry. Each MAF entry can be either an L2 cache or a system field. Both load and stores can create an MAF entry immediately after they check the data cache tag or initial issue. This MAF entry is then forwarded for the further processing by the interface unit, but for the load or store is retired. So the alpha memory is modeled weakly order, so the orderly among references to different memory addresses requires only when the programmer insert memory barrier instructions. In 21 to 94, these instructions drain the internal memory system and bus interface unit. The cache prefetching and management. The memory system implemented cache prefetching instructions that let the programmer take full advantage of the memory system's parallelism and high bandwidth capability. These prefetches are particularly useful in applications with loops that reference large array. In these and other cases where software can predict memory references, it can prefetch the associated 64-byte cache block to overlap the cache miss time with the other operations. The prefetch can schedule far in advance because the block is held in cache until it is used. The table 3 describes the cache prefetch and management instructions. Normal, modify intent, and evict next prefetches perform similar the operation but are used in a different specific circumstances. For each, the processor fills the block into the data cache if it was not already present in the cache. The write hint 64 instruction resembles the prefetch with modified intent except that block's previous values is not loaded. This is useful, for example, to generate a contiguous memory region. So the bus interface unit. The 21 to 64 bus interface unit, BIU, interfaces the internal memory system and external offset L2 cache and tell less of the system. It received MAF references from the internal memory system and responds to with the field data from either the L2 cache on a hit or the system on a miss. It forwarded the victim data from the data cache to the L2 and from the L2 to the system using the 8-entry victim file. It managed the data cache content. Finally, it received the cache proof from the system, performed the necessary cache clearance actions, and respond to the system. The 21.264 implements a write-invalidate cache coherency protocol to support shared memory multiprocessing. So figure 9 shows the 21.264's external interface, and the interfaces to the L2 on the right is separate from the interface to the system on the left, or interconnected on and off the 21.264 are high-speed point-to-point channel. They use the clock forwarding technology to maximize the available values and minimizing pin count. The L2 cache provides a fast backup store for the primary cache. This is the indirect map shared by both instruction and data, can range from 1 to 64 megabytes. The BIU can support a wide range of SRAM, part variant, the different size, speed and latency L2, and including write, synchronous pitch style, and dual data for high speed operation. The peak to L2 transfer rate is 16 bytes every 1.5 CPU cycles. This is balance of the 64 gigabytes per second with 400 MHz transfer rate. The minimum L2 cache latency is 12 cycles using an SRAM part with a latency of 6 cycles, 9 more than a data cache latency of 3. Figure 9 shows that a 21.2064 has a split address out and address in buses in the bus's pin system. This provides balance for a new address request out of the processor and the system probe into processor, and allowed for simple and small-scale multiprocessor system design. The 21.264 system interface is low pin count and a high bandwidth that a high-performance system and 4 or more processors. Broadcast proofs without using a large number of pins. The BIO stores pending systems proofs in 8-entry proofs queue before responding to the proofs in order. And respond to the proof very quickly to support the system. Minimum latency and minimize the address bandwidth required in a common proof response cases. The 21.264 provide a rich set of possible coherence action. It can scale a large-scale system implementation, including directory-based system. It supports all 5 of the standard MOESI, modified on the exclusive shared invalid cache state. The BIU supports a wide range of the system data bus speed. The peak bandwidth of the system data interface is 8 bytes of the data per 1.5 CPU cycles, or 3.2 gigabytes per sec at a 400 MHz transfer rate. The load latency issues of load to issues of the consumer can be as low as 160 nanosecond with a 60 nanosecond DRAM access time. The total 8 of the in-flight MAFs and 8 in-flight victims provide many parallel memory operations to schedule for a high SRAM and DRAM efficiency. This translates into a high memory system performance even with cache misses. For example, 21.264 has sustained in excess of the 1.3 gigabyte per sec usual visible memory bandwidth of the stream benchmark. Dynamic execution examples. The 21.264 architecture is very dynamic. In this article, I have discussed a number of each dynamic techniques, including the line predictor and branch predictor and issue queue scheduling. The more examples in this section further illustrated 21.264's dynamic adaptability. Storing, load, and monitoring ordering. 21.264 memory system supports the full capabilities of the out-of-order execution core, yet maintains in-order architectural memory model. This is a challenge when the multiple loads and stores reference the same address. The register name load cannot automatically handle these read-after-write memory dependencies as it does the register dependencies because it does not have memory address until the instruction issues. Instead, the memory system dynamically detects the problem case after the instructions issue and the addresses are available. This example shows how the 21.264 dynamically adapted to avoid the cost of the load misspeculations. It remembers the first misspeculation and avoids the problem in a subsequent execution by the delaying the load. Figure 10 shows how the 21 to 64 resolve the memory read after write hazard. The source instructions are of the far left, a store followed by a load to the same address. On the first execution of these instructions, the 21 to 64 attempted to issue the load as early as possible before the old store to minimize the load latency. The load receives the wrong data since it issues before the store in this case, so the 21 to 64 hazard detection logic squashes the load and subsequent instructions. After this type of the load misspeculation, in 21 to 64 trained to avoid a subsequent execution by the setting a bit in a load rate tables. Figure 10 also shows what happens on a subsequent execution of the same code. At fetch time store the weight table bit corresponding to a load is set. The issue queue then forces the issue point of market load to be delayed until the prior stores have issued, thereby avoiding the store and load order violation and allowing the speculative store buffer to bypass the correct data to the load. This store wait table is periodically cleared to avoid unnecessary wait. This example load and store load and a case showed how memory system produce a result is the same as in order memory system while capturing the performance advantage of the out of order execution. The unmarked loads issued as early as possible before as many stores as possible, while only the necessary marked loads are delayed. Load hit, miss, prediction. There are misspeculations within a 21 to 64 speculation execution engine. To achieve the minimum 3 cycles integer load hit latency, the processor must speculatively issue the consumers of the issue loaded data before knowing if the load issue or missed in on-chip data cache. This early issue allows the consumers to receive the bypassed data from a load at the earliest possible time. Note that the figure 2 that the data cache stage is 3 clocks after the queued or issue stage. The load cache lookup must happen in parallel with the consumer the issue. Furthermore, it really takes another cycles after the cache lookup to get the hit miss indication to the issue queue. This means that a consumer of the result produced by the consumer of the load data, the beneficiary, can also speculatively issue even though the load may have actually missed. So the processor could rely on the general mechanism available in the speculative execution engine to avoid the integer load data speculatively executed to consumers. However, that requires restarting the entire instruction pipeline. Given the load misses can be frequent in some applications, this technique would be too expensive. Instead, the processor handles this with a mini restart. When a consumer speculatively issued 3 cycles after load and that misses, the 2 integer issue cycles on 4 integer pipes as squashes, or integer instructions that are issued during those 2 integer instructions that are issued during those 2 cycles are pulled back into issue queue to be reissued later. This forces the process to reissue both consumers and beneficiary if the load hits the instruction schedules shown on the top of the figure 11 will be executed. If the load misses, however, the original issues of the unrelated instructions L3 and L4 and U4 and U6 must be re-executed in cycle 5 and 6. This schedule thus is delayed 2 cycles from that dictated. While this 2-cycle window is less costly and full restarting the processor pipeline is still can be expensive for applications with many integer load misses. Consequently, the 21 to 64 predict while load will miss and does not speculatively issue the consumers of the load data in the case. The bottom half of the figure 11 shows the example instruction schedule for this prediction. The effective low latency is 5 cycles rather than a minimum 3 for an integer load hit that is incorrectly predicted to miss. But more unrelated instructions are allowed to issue the slot not taken by the consumer, the beneficiaries. The load miss and load hit and miss predictor is the most significant bit of the 4-bit counter that tracks the hit and miss behavioral center load. The saturating counter decrements by 2 on cycles when there is a load miss. Otherwise incremented by minimized latches in application that often hit and avoid the cost of overspectration for application that often miss. The 21 to 64 treated floating point loads differently than integer load for load hit and misses prediction. The floating point load latency is 4 cycles with no single cycle operation. So there is enough time to reserve the exact instruction that used the load result. The Compaq has been shipping the 21 to 64 to customers since the last quarter of 1998. Future versions of the 2026 21 to 64, taking advantage of technology advances for a lower cost and a higher speed, will extend the alpha performance leadership well into the new millennium. The next generation 21, 3, 64, and 21, 4, 64 alphas are currently being designed that will carry the alpha line even further into the future. Okay. Today I read this paper about the Alpha 21 to 64 microprocessor. Thank you for your time. See you next time.